derivative is a slope, but slope in where? What are we talking about? Say we have quadratic surface like that, somewhere hovering over this xy plane. So this is c is equal to function of x and y, right? Now, say we have a point here, and let's say this is a point right there. And that point is x naught, y naught, z naught. Now we have to take a derivative, meaning the slope. Slope in what direction? Can you imagine the slope of this thing depends on the direction you're walking towards? If you're walking maybe this way, it's more downhill, but if you're going that way, it might be an uphill, and that might be the most uphill from the picture it looks like. So that slope really depends on the direction. You know what I'm saying? So what are we talking about here? Right? So now let's imagine if we cut this thing to some kind of plane that is parallel to this x-axis. Okay? Then what would that look like? Then we are going to see some kind of trace that looks like this, going through that point and then continues on to the other side. You know what I'm saying? Actually, that I don't like that. I want that to be a little more clear. Suppose it looks like that. Okay, so if we have this point, corresponding point on that plane right here, let's say, that's the dot, which is x naught, y naught, if you will, but this is your input, right? Then what happens? What is the slope if you start walking in this direction? Positive. That didn't work out beautifully. Well, I don't know why I'm so anal, but I am. Suppose if you start walking in this positive x direction, that looks parallel now. Then what is the slope that we are measuring, right? That we can imagine, right? So that thingy will look like this. From here, we're going to draw the tangent line somewhere like that, wouldn't we? I mean, the way it's drawn, it looks exactly the same, but this is what is known as the partial derivative in x direction. So we ignore all other rest of the surface if we are just purely moving along this x direction, and then this is a single variable calculus kind of thing, isn't it? Okay, so let's try to figure that out. What would that look like, right? So say, and then here's a notation. One notation is this, partial c over partial derivative of x, that weird looking curvy upside down e looking d. Okay, and then you can actually write it like that, right? Borrowing Leibniz notation, and then you can put f of x and y. And actually, some books actually put, instead of prime, because prime, don't write prime. Prime means we don't know with respect to what, x or y, right? So instead of prime, they actually use subscript, f of x, like that. And you may or may not put this x, y. You know what I'm saying? Okay, all of that means this. All of that means limit of h approaching 0 of difference quotient, f of x plus h, comma y minus f of xy over h. You notice that y is not changing because if I move along this line, my y coordinate stays constant. You know what I'm saying? Right? Our y coordinate doesn't change. It's a purely single variable. So y is constant. X is the variable here. You know what I'm saying? X is the only thing that's allowed to vary, because if we fix our direction, so this is, instead of quadratic surface, this becomes a vector function, if you will. Are we good? Okay, so that's the definition of partial derivative. Will it be nice, like power rule, like last year, or will it be something hideous? What do you say? There's only one way to find out, right? So let's take an example. Say z is equal to y. Let me change the color. Change the color. Okay, it did. I'm gonna change this color too. Really? Change the color. Okay. Z, let's say we have this example, x squared minus x plus xy minus y squared, whatever that surface looks like, okay? Okay, so we're going to calculate partial derivative of z with respect to x. And that, of course, is limit h approaching 0 of x plus h squared plus x plus h y minus y squared. You with me? Minus, and then x squared plus xy minus y squared all over h. Good? Okay. Let's figure that one out. Limit h approaching 0. Since it's too much algebra, can we do most of it in our head? Yeah. See, x squared here is canceled by that x squared, right? So we'll have 2xh plus h squared left. Good. And this xy is canceled by that xy. So we have hy. Good. And then that y squared is canceled by that y squared. So this is it. This is the only thing that's left. Good. You look puzzled. It's been too long since you evaluated difference quotient. Oh, no denominator, that's it. And if we take the limit, h dies, so we have 2x plus 1. Do you see the ramification of this? If we just use the power rule, let's see what happens. 2x, right? This is constant, so x becomes 1, no product rule, y. And this is constant, so it dies. Oh my God. That is so nice, isn't it? So, okay, so let's review and write it down here. So partial z partial x, of course, is equal to 2x plus y. Then guess what this is? Partial z partial y. Now we have enough confidence, right? If we take a derivative of this with respect to y, holding x as a constant, then this will die, and you have x and minus 2y. Do you believe it? Yes, sometimes things are the way you want it to be. You get lucky once in a while, because your life is usually never that nice and easy, right? But once in a while, we get lucky. So what does it look like? What kind of slope are we talking about? Let's go back to the picture. So if our motion, and always think in terms of physics, is from there and moving along in the parallel direction of y-axis, right? And then, first of all, the curve will look like this, right? We are moving along that curve, and then we are looking at the slope of this vector. whatever that vector is. Know what I'm saying? So this is known as the partial derivative, and it is exactly what you want it to be. Okay, that's nice. Well, then you should have a question. Yeah, but there should be a couple of potential questions. Ask that question now. Yeah, but you don't have yeah, but question, you're becoming like zombies. You should have that question about now. Okay, then. Kobe, you have something?
I don't know. I'm gonna take a wild guess and say that do we need to like differentiate anything with respect to z?
No, z is our function. See, last year it used to be y is function of x, so with respect to x, right? So z is our function. So, but I mean, we can think like that too, but I mean, you mean implicit derivative, right? Yeah, actually that happens.
And I don't have a question.
Okay, number one question is, what happens if you want to move to any other direction other than positive x and positive y? Right? What happens if you want to move somewhere here, this way, or like that way? What happens? Like we don't have any way to do that at the moment, right? That's called the directional derivative. Given the direction by angle or by a vector, you can actually calculate the slope of this surface right there too. That's coming future. But baby steps, those are not as nice, okay? But for now, this section at least, enjoy while you can. It's a positive x direction and positive y direction, and that's it. And then we have to imagine if you have a 3-variable function, some function of x, y, and z, then we don't have this kind of, well, like 3D, entire 3D space is our domain, and whatever the positive axis direction, okay? So that's coming. And second question is, what about the second derivative? You know, the concavity comes into a picture now, right? Because this thing has concavity depending on the direction. So how do you take a second derivative? See, last year that was easy because, you know, second derivative looked like this, right? Okay. Or possibly you can have this. But can we cross them? What? So first you take a first derivative with respect to x, and then you take another derivative with respect to y. Yikes! And actually I'm going to move it over, this thing. Nope. Why wouldn't it move? Move. Really? Hell with it. I'm going to erase it. Okay, this thing is written this way. Okay, what that means is take a derivative. I'm messing up all over the place. So this thing means take a derivative with x first, then take a derivative with respect to y. Now, then, of course, we can think about the other case too, right? dx and dy. Oh my God, this is getting so complicated. And that means this. You take a derivative. So this is a right-hand side first, with respect to y first, and then with respect to x. So we have 4 different combinations. Oh my God, no, because 2 variable function. Now, if we move on to 3 variable function, can somebody quickly compute the combination of these things? Suck it up and do it. So, well, this one is easy. You take another derivative with respect to x. You get it? So this becomes 2 plus y. Okay? This one, you take this. We have taken derivative with respect to y, and we take another derivative with respect to y. So, oh my God, I screwed up. This dies, right? Because this is constant, so it dies in the differentiation with respect to x. Now this, if we take a derivative with respect to y, then this x dies, and then we get -2. That much is easy, okay? Say yes. Now the difficult part is the cross terms. Oh my God. So let's see. With respect to x first, we have that here. Now we're going to take a derivative of this with respect to y. Okay? You with me? First x, which we have done it already, and then with respect to y, so we get 1. You with me? And the other one, will the other one be the same thing or not? Well, let's find out. The other one, so we have done this with respect to y first, then we take a derivative with respect to x now, and thus, wait, they are the same thing? Are they always the same thing, or is this a fluke? Did we get lucky? Can life be this good? And in this case, the answer is yes. Sometimes you get lucky twice in a row. They are always the same thing. There's a theorem in the book, and I'm not going to prove it, but the order doesn't matter. So instead of 4 different combinations, there are really 3 different second derivatives. Okay, and let's review the notation. This is f sub x, right? And this is f sub y. So guess what they call this one? This is fxx. And this is fyy. Right? And this is called xy, yx, xy. It really doesn't matter because they're the same thing. You know what I'm saying? And then we have this theorem, xy is same as fyx. So it doesn't matter which way we write it, they're the same. Oh, thank God, huh? How about that?